Hello and welcome to yet another lecture on the binomial theorem. In the previous lectures, we've seen several identities which relate the binomial coefficients. From this lecture on, we will look at some offbeat results which use the binomial theorem. So recall, the binomial theorem is given as follows: x plus y the whole power n equals summation r equal to 0 to n cr x power n minus r y power r, where cr denotes ncr. So the first result we'll be looking at today is the following. It says, suppose 2 plus square root of 3 the whole power n equal to I plus f, where I and n are natural numbers and 0 is less than f is less than 1. We are asked to show that I is an odd integer and also that 1 minus f times I plus f equal to 1. So at first sight, this result seems fairly strange because so far we have not seen anything of this character, but as we shall see shortly, this does use the binomial theorem in a very strong way. So you're given that 2 plus 3 the whole power 2 plus square root of 3 the whole power n is some integer plus a fraction term. So you can clearly use the binomial expansion of 2 plus square root of 3 the whole power n, but you would have several terms which have square root of 3 raised to some integer powers which may not be integers themselves. So that doesn't seem like a very promising route to derive the value of I. So I is essentially the floor of square root of the floor of 2 plus square root of 3 the whole power n. So we shall use the following trick. So what if you add 2 minus square root of 3 the whole power n to 2 plus square root of 3 the whole power n? So what does this give us? So in one of our previous lectures, we've seen that x plus y the whole power n plus x minus y the whole power n can be expressed in a more compact form, and so let's do that. So this is equal to 2 times c0 2 power n square root of 3 power 0 plus c2 2 power n minus 2 square root of 3 power 2 and so on. So this is a result which we've seen in one of our previous lectures. So what this serves to illustrate is that this summation of 2 plus square root of 3 the whole power n and 2 minus square root of 3 the whole power n is 2 times this expression, and you notice that each term in this expression is an integer because all the CRs here are integers, 2 power n minus r's are integers, and square root of 3 raised to an even power is always going to be an integer. And so you notice that this term within the parentheses is an integer, and this whole integer is multiplied by 2, and so this means that this is an even integer. So we have that 2 plus square root of 3 the whole power n plus 2 minus square root of 3 the whole power n is an even integer. Can we say something about 2 minus square root of 3 the whole power n? We are given that that n is a natural number, and so since 2 minus square root of 3 is between 0 and 1, square root of 3 is 1.7 something, and so since this is between 0 and 1, we have that this number raised to any natural number is going to be still between 0 and 1. So what this tells us is, suppose so now we've recognized that 2 minus square root of 3 the whole power n is a fraction. Let's call it f bar, and so this is between 0 and 1, and so we know that since 2 plus square root of 3 the whole power n is denoted by I plus f, we know that I plus f bar equal to even integer. This is what we've derived from this expansion. So since f and f bar are both strictly greater than 0, this implies, and I is an integer, this implies that f plus f bar should be equal to 1 and I is an odd integer. This is the only possible explanation for I plus f bar being an even integer. So we've derived the first result which we wanted to show, which is that I is an odd integer based on this analysis. Our next result is somewhat strange. It says that 1 minus f times I plus f equal to 1. But notice that we've derived that f plus f bar equal to 1, and so this implies 1 minus f is nothing but f bar, which implies we want to show that f bar times I plus f equal to 1. So you can rewrite the left hand side of this expression as 2 minus square root of 3 the whole power n, which is f bar, and I plus f is nothing but 2 plus square root of 3 the whole power n. Now we have a minus b the whole power n times a plus b the whole power n, and you can expand this product as 2 square minus square root of 3 square whole power n. This is nothing but 1. So this problem illustrates an offbeat application of the binomial theorem, where the application is not evident at the beginning, but notice that we realize that 2 minus square root of 3 the whole power n, the conjugate of 2 plus square root of 3 the whole power n, lies between 0 and 1, and we used the binomial theorem to derive that the floor of 2 plus square root of 3 the whole power n is an odd integer, and we also showed this additional result. So let's look at a related example where we're given that p equals 6 times square root of 6 plus 14 the whole power 2n plus 1. So as to show that the floor of p is an even integer and floor of p and p times p minus floor of p, this is nothing but p times the fractional part of p, equal to 20 power 2n plus 1. So this is the result we're asked to show. So once again, we consider 6 times square root of 6 plus 14 the whole power 2n plus 1, and 6 times square root of 6 minus 14 the whole power 2n plus 1. But this time, instead of adding these two terms, we're going to subtract these two terms. And we note that 6 times square root of 6 minus 14 is again between 0 and 1. So 6 times square root of 6 minus 14 power 2n plus 1 is still going to be between 0 and 1. So we're subtracting a fraction from p. So once again, using the binomial expansion, you can show that this difference is going to be nothing but 2 times 2n plus 1 c1, 6 times square root of 6 power 2n times 14 power 1 plus 2n plus 1 c3, 6 times square root of 6 power 2n minus 2 times 14 power 3, and so on. So from this step, it is clear why we've subtracted 6 times square root of 6 minus 14 power 2n plus 1 instead of adding it, because now we want the square root of 6 to be raised to even powers. We only want those terms to survive, and we don't want the terms which have square root of 6 appearing to survive. So notice that all the terms inside the parentheses are now integers, and so we have that this difference is nothing but 2 times an integer, and so this difference is an even integer. So we've shown that p minus this fraction is an even integer, and so let 6 times square root of 6 minus 14 power 2n plus 1 be f bar, and 6 times square root of 6 plus 14 power 2n plus 1 be equal to I plus f once again, where I is the integral part and f is the fractional part of p. So we have I plus f minus f bar is an even integer from the previous result. So since f and f bar are both between 0 and 1, this can only be true if I is an even integer and f equals f bar. So this is the only case in which this constraint can be satisfied, and so we've shown that I, which is nothing but the floor of p, is an even integer. So this is nothing but the floor of p. And we've also shown that f equals f bar. So our second result asks us to show that p times the fractional part of p is 20 power 2n plus 1. We can re-express that as p times f, which is nothing but I plus f times f equals 20 power 2n plus 1. So we would like to show this result. We've seen that f is nothing but f bar from the expansion, and so we have that this is nothing but I plus f times f bar, which is equal to 6 times square root of 6 plus 14 power 2n plus 1 times 6 times square root of 6 minus 14 power 2n plus 1. And you can once again expand this expression to be 6 times square root of 6 whole square minus 14 square power 2n plus 1. And this gives us 216 minus 196 power 2n plus 1, which is 20 power 2n plus 1. So this shows the result we wanted to prove, that p times the fractional part of p is 20 power 2n plus 1. And once again, the idea was to somehow re-express p times the fractional part of p as the product of conjugates, in this case 6 times square root of 6 plus 14 and 6 times square root of 6 minus 14, and the result then follows easily. So once again, we've seen an application of the binomial theorem where we are asked to derive the integral part of a given irrational number raised to a binomial exponent, and we've seen how to do that using the binomial expansion. Now let's look at the following multiple choice question, which is similar to the examples we've seen, and it asks us to derive the greatest integer less than or equal to square root of 2 plus 1 whole power 6. And the options are 196, 197, 198, 199. So in this multiple choice question, you're not only asked to find whether the floor of this number is even or odd, but you're asked to find the exact value. And the previous analysis, we've ignored what the actual value is. We are only concerned with whether the value was even or odd, whereas in this example, we're asked to derive the actual value. So once again, let's call square root of 2 plus 1 to the whole power 6 to be an integral part plus a fractional part. And we're going to look at square root of 2 minus 1 to the whole power 6. And once again, square root of 2 minus 1 is between 0 and 1. And so we can call this to be a fractional part f bar. So this is a fraction between 0 and 1. So since we only want the even powers of square root of 2 to survive, we're going to add these two expressions. And that gives us 2 times 6c0 square root of 2 power 6, 1 power 0, plus 6c2 square root of 2 power 4, 1 square, plus 6c4 square root of 2 square, 1 power 4, plus 6c6 square root of 2 power 0, 1 power 6. You can expand this to get 2 times 8 plus 15 times 4 plus 15 times 2 plus 1, and this is 198. So this is so we have that I plus f plus f bar equals 198. So similar to the previous example we've seen, this implies that I equals 197 and f plus f bar equals 1. So the right answer is that the integral part of square root of 2 plus 1 to the whole power 6 is 197. And that's all we're asked to show in this example. So that's it for this lecture. We've seen several offbeat applications of the binomial theorem. In the next lecture, we will look at certain divisibility results based on the binomial theorem. Thank you for your attention. I hope you enjoyed watching this lecture. Stay tuned for more lectures on the binomial theorem.